Okay, so let's start off with some observations first to get you guys ready.
In Florida, there's a special lab studying lightning. ABC's Bill Blakemore went to pay a visit.
At any one moment, there are about 2,000 electrical storms on our planet. It's a constantly crackling ball of lightning, about 100 bolts a second, striking people, houses, power line, airplanes.
Normal commercial plane about twice a year.
A given plane.
Yeah.
Electrical engineer Martin Newman is in league with Jove himself. His 100-acre lab in Florida is plugged into the biggest source of electricity there is. This is the only full-service lightning study center. One experiment here, how to protect planes. They rarely crash when they're hit, but their navigation systems can get knocked out by lightning bolts current.
We can map the whole electric and magnetic field that a plane would be bathed in. Everything's attached.
Newman pulls thunderbolts down from the sky by firing rockets, each trailing a wire as high as the Empire State Building. The wire attracts lightning from miles up that follows it back to the ground.
Starting countdown. 5, 4, 3, 2, 1, fire. Lightning!
High-speed cameras capture each microsecond, revealing not just one stroke, but a second, then a third and fourth, and a rare glimpse of a beaded effect that's still a mystery to science. But they did measure the electricity right next to the lightning bolt, vital data for redesigning airplane wiring for bad weather.
There's some storms in the Midwest that have produced nearly 100 lightnings a second.
Newman's experiments have already helped to protect runway lights from lightning. He's also hitting power lines with lightning, learning to protect them. And he's built this house, which he's hitting with lightning, to discover ways to make your wiring safer.
That's one of the intents, is to make sure that we can have a safe house, that you can sit in here and watch TV while we strike it with lightning.
Right. But don't try this on your house. It's better to leave these experiments
Fire.
to the experts. Bill Blakemore, ABC News, at the University of Florida's Lightning Center.
All right, lightning!
Near Gainesville.
So what's lightning?
Electrical arc.
Okay, so electrical discharge, you give yourself 2 points for that one. Okay, so next logical question is, what is electrical discharge?
The transfer of electric energy.
Okay, so transfer of electrical energy. Okay, so what's energy and how do you transfer it?
You change it into different forms.
Okay, Lucas, I'm gonna give you 5 points. I'm just gonna move on. Okay, so electrical discharge is your lightning. So what causes lightning? Okay, real fast. If you know the answer, just jump in. Okay, so what causes lightning? No answer. So lightning, where does it come from? How about the heat? The temperatures rise up to the temperature at the surface of the sun, guys. So it gets really, 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 really hot. So given that, where does the heat come from? So where do you get the light from? Where do you get the heat from? How about the sound? You get the thunder. So where do you get the sound from? So what causes the electrical discharge? Does it start from the ground or does it start from the clouds?
Starts from both, right? Like,
okay, when you say both, you're covering everything. You're covering your butt pretty well.
Well, it comes up from the ground and then it comes down from the clouds, like at the same.
Okay, if you had to pick one, which one would you pick?
The cloud.
Okay, you pick the cloud because it looks like it's coming from the clouds, right?
Yeah.
All right. I mean, that's a fair assessment that the lightning is coming from the clouds, and there's some who will argue that it's actually coming from the ground, and there's some who will argue that it's coming from both directions. So what's causing lightning? What's happening between the ground and the clouds that initiates lightning?
They have a difference in electric potential.
Okay, so they have a difference in electric potential, and the electric potential is
just like free electrons. Maybe, I don't know.
All electrons are free, right?
Yeah.
Are they?
I don't know.
You don't
That's
know.
what I'm hearing.
All right. So what causes? You're saying that Matthew, you're the one who's talking, right?
Yeah.
I'm gonna give you 5 points for that one. So Matthew says that the potential difference between the clouds and the ground is responsible for the lightning. What's potential difference and what causes it? How do you build up the potential difference so that you get lightning? I'm moving forward. Most people struck by lightning, do they die or do they survive? What do you guys think?
They're kind of dead.
I'm sorry, what?
They're like dead, most likely.
Most likely they're dead?
Yeah, I mean,
and least likely that they will survive?
No.
Guys, what makes the news is the bad stuff, right? People getting struck by lightning and dying is what makes the news. What makes it to the news usually. So if that's the case, believe it or not, most people struck by lightning do survive. So what makes it so survivable? You wouldn't think that you would survive that, but most people do, actually. So lightning, so far, what do we know? You guys said it's an electrical discharge. I asked you what an electrical discharge was, and there was no satisfactory answer for that one. What caused lightning? Matthew said potential difference. I said, what's the potential difference? Once again, silence. And the lightning, where does it come from? Does it come from the clouds or the ground? Some said it's going to be coming from the ground. Some said it's going to be coming from the clouds. Some will say it's going to be both. And most people struck by lightning will survive. So the question is, where do you get the light from? Where do you get the heat from? Where do you get the sound from in lightning? And that's not it. It gets even more interesting than that. I love this one. Notice that you got running water, and all of a sudden it becomes attracted to a charged comb. How does a charged comb attract water?
Because water is a polar molecule, and it will depending on what charge the comb has, the molecules of the water will shift accordingly, so that the opposite charge is facing, so it will bend towards the comb.
Okay, so Lucas, I'm gonna get back to you again. Imagine that this comb is negatively charged. What does it mean? What does it mean to you when somebody says it's negatively charged?
It means it has an excess of electrons.
It's got excess of electrons, right? So which means that it's going to be negatively charged. It's mostly made up of excess electrons. That's what you're saying. Okay, so how does that attract water again?
Because water is a polar molecule, it has positive and negative sides. So the positive side of the water molecules is going to be attracted to the negative charge of the comb.
All right, so let me ask you this question. Is water neutral or not?
What do you mean neutral?
What do you mean by polar?
I mean that one side of the water molecule is positively charged and one side is negatively charged.
Okay, so when I say neutral, what does it mean to you?
That it would not have any distinct poles. It would kind of just not really have any net charge.
So what's the net charge of water? Is it positive charge, negative charge, or neutral?
I guess by your definition, I would say neutral then.
Okay, so how does a negatively charged comb attract something neutral?
Doesn't it have to be positive because the ground is positive and the electrons up in the cloud when lightning strike is negative? So you have more negative that go toward the bottom of the cloud, and you have positive on the ground as the lightning strikes. So I would say water is negative, right?
Okay, Caleb, what did you say? Get back to the clouds. Forget the water. What is it that you were saying about the clouds?
Doesn't the electrons, the negative electrons in the cloud, they go more toward the bottom of the cloud. When they strike, they get closer to the earth. And the ground is positive, has positive electrons, and then that's when you get the strike. So here, if the comb is negatively charged, I would say that the water is positively charged.
Okay, Caleb, I'm going to give you 5 points. Lucas, I'm going to give you 10 points for something that I will explain later on. We'll get back to those discussions one more time.
It's one of the very early strikes that we had where it struck the nose boom, as many of our lightning strikes did, and it then swept up over the top of the windshield, down that metal bar that was over the top of our heads in the canopy. And I could just happen to look up, and I could see helical chunks of plasma as the lightning channel broke apart as it flew back over the top of my head.
The onboard camera revealed something totally unexpected. The plane wasn't just intercepting lightning, it was actually triggering it by interfering with the electrical field inside the cloud.
So the airplane is being struck by lightning. You're on the inside and you're safe.
Nose boom, as many of our
we had a discussion regarding this. So why are you safe when you're on the inside? You guys came up with 3 explanations for it. Number 1, the outside is metal, right? That's the conductor. Number 2, you're not in direct contact with the metal on the inside because you got some insulating material between you and the metal of the airplane. And some of you guys said that either the airplane is grounded or not grounded, whatever that means. And that's the reason why you're safe. So I ended up changing the scenario for you guys. I said, what would happen if you were to get rid of the insulating material on the inside so you can in direct contact with the metal on the inside? So what would happen? Most of you guys thought that you would get shocked. I said, no. And then I said, what would happen if I were to put you on the outside of the airplane while it's getting struck by lightning? Do you think you would get shocked? And most of you guys thought that you would get shocked. I said, no, absolutely not. If you're not taking a direct hit, you would be perfectly fine.
Jerry Stiller is mad.
Man, I'm going crazy!
He bought this plastic wrap to keep his fruit salad fresh.
Only I can't get it from here to the food!
Jerry, you should have bought Glad Cling Wrap. Glad unrolls smooth and easy and clings tight when you need it to.
Comes out easy!
Yep.
And cleans tight!
Absolutely.
Hello, Glad Cling Wrap!
Don't get mad. Get Glad. Need it to.
Jerry Stiller, amazing comedian. Passed away
Tight.
last week. All right, so speaking of a plastic wrap, why does it cling so tight to glass? It's going to cling tight to glass. Porcelain, not so much the metal pots. So why is it so clingy? All right, guys, I got news for you. This thing is going to be negatively charged, whatever that means to you guys. So plastic wraps are negatively charged. If that's the case, why is it that they cling so strongly to glass?
If it's negatively charged, does that imply that the glass is positively charged?
Okay, absolutely. You can make that judgment call, right? All right, so if you go by that logic, Isabella, I'm going to give you 5 points for saying something like that. Which means that it's going to be able to stick to porcelain. Does this mean that porcelain is also positively charged?
Probably, yeah, but not metal.
Okay,
I don't think
but the metal, it's not going to stick to metal because metals are
negatively charged.
Metals are negatively charged
or neutral.
or neutral. Okay, so that's perfectly fine. All right, so what's the meaning of something being positively charged, negatively charged, or neutral? That's what I'm getting at. Or how do you make something positively charged, negatively charged? Oh, I love this picture. Beautiful smile. Look at the hair, though, standing up. This is high ground, Square Mountain. I was there over the summer teaching over at COS, the College of the Squares. And high ground versus the low ground, which one is more likely to be struck by lightning?
High ground.
High ground, right? Why?
It's easier to get to.
It's easier to get to. That's not bad. High ground versus low ground, which one is going to be more likely to be struck by lightning? Most of you guys will say it's high ground, right? Because the proximity between the ground and the clouds is actually relatively small. So more than likely it's going to strike high ground. All right, so take a look at the picture. Her hair is rising up. Her brother thought that it was funny. Snapped that picture, and shortly after they left, the lightning struck one person, that a couple of people got injured. All right, so this is one of the telltale signs that the lightning is about to strike. Why is it that her hair is rising up? Furthermore, if high ground is more likely to be struck by lightning, why then the Chicago's Sears Tower or Big Willie is not the one that's getting struck by lightning 100% of the time? Why is that? That logic is just breaking apart, guys. You've been told ever since you were born that the high ground is more likely to be struck by lightning than the low ground, which implies that the tall structures, the buildings, should be struck by lightning 100% of the time. And yet this time, notice that the lightning is completely missing the Chicago Sears Tower and hitting a building which is about a mile out. All right, this is the building I used to work at. All right, so these are the questions that we will get to explore. Let's talk about this guy, one of my heroes. It's Ben Franklin. Speaking of Ben Franklin, why do we have his picture on a $100 bill? Does anybody know? Okay, at this point, we have to have a conversation. Why do we have his picture on a $100 bill? Any ideas, any suggestions?
It's his favorite number.
100 was his favorite number. I don't know about that. Ian, what are his contributions to anything?
He was a postmaster general, wasn't he?
He was. Give yourself 2 points for that one. So he was a postmaster general. That's the reason why we got his picture on a $100 bill, right?
He did like experience with the kite and the lightning rod.
Yeah, he did. He did. And is that the reason why we got his picture on a $100 bill?
I mean, it's probably one of the.
No, he was flying a kite in an electrical storm, right?
Yeah.
Why did he do that? What was the purpose of it? He must have been trying to prove something. Why did he do that? Did he actually do that, or do you think he lied about it?
Didn't he tie like a key to the end of the kite, and he wanted to prove that metal was more attracted to lightning than anything else?
Isabel, I'm gonna give you 5 points for that one. Does metal attract lightning more than glass?
Yeah, because it's a better conductor, right?
It's a better conductor, right? If it's a better conductor, does this mean that it's more attractive to lightning?
Maybe.
Okay, lightning rods. Alec, let's talk about lightning rods. What's the purpose of a lightning rod?
They're all metal, right?
They're all metal. And the lightning rod, what's the purpose of it? The purpose of a lightning rod, is it to attract or repel lightning?
Attract lightning.
Attract lightning, right? And they're made up of metal, right?
Yes.
So given the fact that the lightning rods are made up of metal, does this mean that the metal is more attractive to lightning?
Yeah.
Okay, so, and who came up with the lightning rod?
Benjamin Franklin.
Oh my God, Ben Franklin himself. He came up with it, right? Is that the reason why we got his picture on a $100 bill? Because we appreciate people who come up with interesting inventions? Do we really care?
I mean, all
right, guys, let me ask you this question. All of you guys are from Chicago, around this area, right? What is the highest accolade you can earn in sciences? Highest accolade that you can earn in sciences is known as Oscars, right? Somebody's going to make a movie about you, and then that's the highest accolade that you can earn.
Nobel Prize.
Stephen Hawking has the highest accolade because somebody won an Oscars for his movie. What was the name of that movie?
Theory of Everything.
Give yourself 5 points. Theory of Everything. All right, so that's what happens in appreciation. People make a movie about you. That's the highest accolade. No, guys, what's the highest accolade that you can earn in sciences?
The Nobel Prize.
Nobel Prize. It's not the Nobel Prize. It's the Nobel Prize. Give yourself 5 points for saying it the right way, not the Trump way. So it's the Nobel Prize, right? All right, so given the fact that the highest accolade you can earn is the Nobel Prize, let me ask you a dumb-ass question that you may or may not be able to answer. I think I know that you won't be able to answer it. That's the reason why I'm going to
I can answer it.
All right, we'll try. You can Google it. All right, so what is the name of the guy who won the Nobel Prize in physics 3 or 4 years ago who was from Chicago? All right, take all the time you need. I'll give you 2 more seconds.
Pete.
All right, time's up. Not a single person. Okay, who here does not know who Kim Kardashian is? Every single person knows Kim Kardashian. And not a single person knows who won the Nobel Prize in physics. The guy from Chicago. I wonder why. Because we don't care.
Those are
No one cares. No one cares if you're a scientist, if you have a Nobel Prize. Not in the United States. No one cares. Culture is not a big thing in the United States, guys. Anything related cultural is not a big deal. Soccer is not a big deal. Physics is not a big deal. Blah, blah, blah. All right. You could be a physicist. You can win the Nobel Prize. No one gives a shit. All right. Originally, I'm from Turkey. If I were to win the Nobel Prize in physics, everyone in Turkey would know who I am. Not in the United States, though, because no one cares. Science is not considered a cultural thing. As long as you can money doing it, all right, that's as far as you will go. You're going to be able to make money, but you're not going to get the recognition that you deserve. Who won the Nobel Prize in physics 3 or 4 years ago? The guy from the University of Chicago? I have no idea. Do I care? Not really. All right, because I've been here for way too long, guys. No one cared about Franklin. It's science. During the colonial times either. No one gave it, no one thought very highly of it. It was considered to be one of the best physicists who ever lived in Europe. It was considered to be one of the best philosophers who ever lived in Europe, not in the States, not in the colonies. So he must have done something really worthy so that we have his picture on a $100 bill. What did he do? Any ideas? By the way, guys, we're not even
Declaration of Independence.
We're not even doing any physics. We're talking about history. And
also
Rohit. Let's get back to what Rohit said.
Yeah, he was like one of the founding fathers.
He's one of the founding fathers. What else? He's not the only one. What else?
He signed the Declaration.
He signed the Declaration. What else? He did a lot more than signing the Declaration. What did he do?
He helped write it.
He helped write it. He helped shape it. And he was the guy behind the ideals of democracy. He was the guy behind the ideals of unification of these colonies into one. What else did he do? If the United States was a cult, a religion, he would have been its prophet. It's weird. So what's the difference between the United States and Canada? They look the same from outside. The United States is a superpower. Canada, not so much, right? I wonder why. Because the United States is built after the ideals of these people. Franklin was the head master in this case. What else did he do? So the War of Independence. How did the colonies end up winning the war? What happened?
Well, so
we got the guy.
Also,
go ahead.
Okay, so Franklin, of course, he enlisted the help of the French. That was like one of the big things he did. He was able to kind of get the French on our side, and then the French were a big help in that war because they were a superpower at the time. And then I guess also after he was like the ambassador to France and did a lot of fun stuff there. So.
Okay, all right, Bailey. I like your take on that one. All right, so Bailey, what's your major?
Computer engineering.
Computer engineering. So you kind of like history, right?
Yeah.
All right, so here's what he did. 2 superpowers, France and England, always at war. They decided to solicit help from France, right? So he goes to France, and then the French decided to join the fight immediately, correct? Yes or no?
Probably not.
Nah, not a chance. All right, so you got these people in the colonies, they're trying to start a fight against England. England is a superpower, and you got a bunch of people in the colonies, they're trying to fight against the superpower. It's not gonna work out, right? So they organize and they put together an army, and they're losing every single battle just about. So at that point, they decided that they needed money and they needed some military help from France. So they end up sending Franklin to France. Franklin is well known. This guy is an idol. He's a physicist. Physics is something which is, science is something which is highly appreciated by Europeans. He's also a philosopher in the sense that he's got these ideas of democracy. So he was well received in France, except until Washington started to win a couple of the battles here and there. The French did not take Franklin seriously. After a few victories, immediately they noticed that there was potential, so they decided to invest. So they invested a lot of money, they invested a lot of troops. And then eventually, obviously, Washington did its job, and then Britain decided to give the colonies their independence. Who sat down with British to negotiate the settlement? Does anybody know? What was on the table with British? Settling the War of Independence. Once again, guys, it was Franklin who did the final negotiations against Britain. So needless to say, British really didn't like him that much. All right, so do you understand why we have his picture on $100 bill? Because of that. Also, he was considered to be the best physicist of his generation.
Franklin's curious mind now becomes intrigued by one of the great scientific mysteries of the 18th century, the phenomenon of electricity.
Never in my life has anything so totally engrossed me. While I was making experiments and then repeating them for my friends and acquaintances who come in crowds to see them, I don't have a moment for anything else.
In Franklin's day, electricity was much more of a puzzle than gravity had been a century earlier in Newton's time. Everybody was familiar with things falling and all, but electricity, it was just a matter of rubbing something and getting some sparks. Where did this come from? Very mysterious.
For Franklin, the pursuit of electricity started as a game. there was an itinerant Englishman who went from town to town showing gadgets that produced scintillas and sparks and could do things.
In one popular demonstration, a group of people hold hands and then receive a collective shock from an electrostatic generator. This game is performed by people around the world.
With the kind of mind and the curiosity he had, Franklin wanted to go beyond the amusement.
The great thing about every one of these Paula tricks, the simple phenomena of attraction, repulsion, was why. Before Franklin, no one had any clue.
Franklin puzzles over electricity for almost 10 years. Why is a stream of water attracted to a charged glass rod? Can you kill an animal with an electric shock?
How about a person? If you get a plastic rod and then rub it against animal fur, if you have two of them, they will repel. If you rub the same rod against silk, they will attract. And all of a sudden, we have this phenomenon. Charged objects will either repel or attract each other. The question is, what caused the repulsion and what caused the attraction of these charged objects? Franklin said that we can actually explain this phenomenon by assuming that there are two kinds of charges.
At the time, everyone assumed that electricity was some mysterious force created by rubbing two different substances together. Through experimentation, Franklin proves that in fact, the friction does not create electricity, it simply moves a charge from one body to another. When these charged bodies are brought close together, the result is a spark. Electricity flowing through the air.
This theory was based on the concept of an electric fluid, like an electric current, and that this could exist in bodies in a surplus or a deficiency. He called one state plus or positive and the other minus or negative.
Before Franklin, people had no idea what electricity was or how it worked. After Franklin's fundamental insight, the phenomenon of electricity could be understood and harnessed as a force to change the world.
In order to explain what caused attraction and what caused repulsion, Franklin came up with two different charges. He said that assuming that there are two different charges, you can explain attraction as well as repulsion. He thought of electricity as an electrical fluid. Excess of the fluid, he said positive. Deficiency of it is negative. Positive charges and negative charges, like charges will repel, the unlike charges will attract each other. Okay, we know today that these charges are real. It's not a deficiency or excess of it. So unlike charges will attract, like charges will repel each other. And we will find these charges inside atoms. Atoms will have equal number of positive and negative charges. Positive charges will occupy the center of an atom, that's known as the nucleus. The negative charges will move about the nucleus according to classical theory, like the way the planets do about the sun. All right, so the positive charges are known as protons, the negative charges are known as electrons. All right, so here's the classical atom. You have the positive charge right at the center, and you have the negative charge or charges moving about the center. Okay, E means unit charge. Unit charges could be positive or negative. So you have positive unit charges and you got negative unit charges. Positive unit charge is known as a proton. The negative unit charge is known as an electron. Unit charge is going to have a value which is extremely small. This is going to be 10 to minus 19 Coulomb. C is going to be Coulomb. Coulomb is the name of a Frenchman who's got some significant contribution in electrostatics. The value of a unit charge, positive or negative, is this. It's 1.602 times 10 to minus 19 Coulomb. First measured here in Chicago in 1905 by someone named Robert Millikan, who won the Nobel Prize in 1923. All right, so that's the unit charge. So you got positive charges, you got positive unit charges, you got negative unit charges. And the unit charges are going to be found inside atoms. All right, so speaking of charges, let's get back to the lecture. These charges cannot be created or destroyed. Smallest unit charge, the negative one that you can have, is an electron, according to classical physics. And you cannot break electron into something smaller than itself. All right, so the charges cannot be destroyed, they cannot be created. And everything is made up of unit charges. Question number one, what are unit charges? We got two, positive and negative. Positive ones are protons, the negative ones are electrons. Question number two, what are the experimental proofs? What's the experimental proof that we got two different unit charges? Experimental proof is charged objects will either attract or repel each other. You can explain the attraction as well as repulsion phenomena by assuming that there are two kinds of charges. Like charges will repel, the unlike charges will attract. Given the fact that we got unit charges, so what's the meaning of a net charge if that's the case? Net charge is the sum total of all the charges that you have. Number of unit charges that you may have is known as the net charge. Case in point. All right, just imagine that this is plastic. And then I'm going to charge it up negatively. All right, so let's drop some charges on it. 1, 2, 3. Notice that we got 4 negative charges. All right, so the net charge is the sum total of all the charges that you have on it. So Q is known as the net charge in this case. So that's your net charge. So the unit charge is E. Lowercase c is going to be your unit charge. Q is your net charge. In this case, N that you're looking at is the total number of charges that you have. So in this case, N is going to be 4. Obviously, you got 4 negative charges. So this becomes your net charge, sum total of all the charges that you have. So the next question is, remember the Coulomb in the beginning of the lecture? I said it's negatively charged. So how do you charge something up positively or negatively, given the fact that you cannot create or destroy charges? How does that happen?
Friction.
Okay, you can charge something up positively or negatively by transferring charges, right? Before you transfer charges, you have to separate charges, which means that you have to actually knock electrons out of atoms. The process of separating charges or liberating charges from atoms is known as ionization. So process of liberating electrons from atoms is known as ionization. There are 3 ways you could do that. One of them is friction. Somebody mentioned that already. Give yourself 2 points for that one. The other one is heat. And then the last one is light. So through friction, heat or light, you can actually liberate electrons from atoms. The most obvious one is the friction. You can get the comb and then rub it against silk. Forget silk, animal fur. It's going to become negatively charged. Or if you rub it against silk, it's going to become positively charged. So friction is one way of doing it, but that's not the only way of doing it. All right, so let's talk about lightning, for example. Before the lightning takes place, the clouds need to become ionized. So how do we ionize the clouds? What process is responsible for ionization of the clouds?
I would guess heat.
All right, so you are guessing that it's going to be heat.
Or light.
Okay, guys, so what happens inside the clouds? Let's just talk about that. What is the process responsible for the ionization of the clouds? Notice that the top of the clouds will become positively charged and the bottom of the clouds will become negatively charged at some point. But before that happens, the negative charges need to become separated from the positive charges. Top becomes positive charge, the bottom becomes negative charge. Okay, so what are clouds made up of?
Water.
It's water. They're not made up of cotton. If that's the case, where do you think we're getting the cotton from? It gets kind of confusing.
Ice.
The clouds are made up of, very good, guys. It's the water vapor. Okay, and speaking of the water vapor, what happens inside the water vapor that causes ionization? So let's focus on that one. So there are 3 ways you can ionize the clouds, right? Friction, heat, or light. Which one is responsible for the ionization of the clouds as far as you're concerned?
Friction.
All right, so I heard friction, I heard heat. How about light?
That's my vote.
Okay, either way, you give yourselves 2 points each. All right, so does lightning ever happen at night? Yes or no?
Yeah.
It does, right? So if that's the case, what would be the light source? You can say the stars, you know, it's not going to work. You can say the moon, not so much. So let's rule out light as the main reason for ionization. All right, so now we got 2 that we can focus on. Is it the heat or is it the friction?
Heat.
Let's talk about heat. Okay. Do you think it's really hot inside the clouds or do you think it's really cool inside the clouds? What do you think? All right, so next time while you guys flying, all right, just when they give the altitude information, they also give you the temperature information. When you're 30,000 feet up, you know the temperatures are sub-zero temperatures, right? But the clouds, usually you won't find clouds at 30,000 feet up. When you start to rise up, when you start to gain altitude, you know the temperatures start to drop, right? But then inside the clouds, the temperatures are about 32 degrees or less. So what do you have at 32 degrees or less, usually?
Ice.
Yeah, I mean, if you got water vapor, it's going to crystallize, right? So what you have, you're going to have ice crystals. All right, so which means that inside the clouds, it's usually not hot. It's somewhat cold inside the clouds. And then the ice becomes, the water becomes crystallized. So what happens inside the water crystals? Ice crystals, water crystals, ice crystals. Okay, so they're going to move up and down. So there's going to be a lot of friction. So what creates the initial ionization of the clouds? It's got to be the ice crystals rubbing up against each other.
Although lightning can reach temperatures exceeding 50,000 degrees Fahrenheit, these superheated bolts are actually created by ice.
Told you.
Inside clouds, air currents carry water droplets to...
All right, so we got 2 minutes to go, so I'm just going to torture you for the next 2 minutes. All right, so the top of the clouds will become positively charged. The bottom of the clouds will become negatively charged, right? So what caused the top of the clouds to become positively charged and the bottom of the clouds to become negatively charged? They notice that the Earth is positively charged. Yeah, this is so cute. But I got news for you. The Earth is actually initially negatively charged. Earth is not positively charged. It's initially negatively charged. Only after the separation of the charges, the Earth magically becomes positively charged. So what causes the separation of the charges inside the clouds? That's friction, right? So why is it that the top of the clouds become positively charged and the bottom of the clouds negatively charged? So what causes the further separation of these charges?
Oh, there's more electrons, so it want to be heavier. Very slightly.
I get a question mark here. This is so cute. Electrons are heavier. All right, give yourself 2 points for that one. Electrons are actually almost 2,000 times lighter than the hydrogen ion, so the gravity doesn't explain it. I'll give you 5 points for that one. All right, so okay, so the torture is over, guys. It's one of those mysteries. No one knows the real reason. All right, it's been around for, this question has been around for over a century. We a bunch of theories, and none of these theories explain everything that we know about lightning. All right, everything falls short at some point. One of the best places where you could go check to see what's going on is my favorite source, which may or may not be available to the public at large, which is otherwise known as Wikipedia.
Rising ice crystals. During these collisions, electrons break free from the ice crystals and bond with the hailstones. The rising ice crystals create a positive charge at the top of the cloud, while the falling hailstones create a negative charge at the bottom.
Okay, guys, so this is the explanation you will get from Wikipedia. This is one of the explanations that you will find. Does anybody see anything wrong with this explanation?
The heavier hailstones. Air currents carry water droplets to higher, colder altitudes. As the droplets rise, they freeze into ice crystals. These crystals join to form hailstones. The heavier hailstones drop through the cloud, colliding with more of the smaller rising ice crystals. During these collisions, electrons break free from the ice crystals and bond with the hailstones. The rising ice crystals create a positive charge at the top of the cloud, while the falling hailstones create a negative charge at the bottom.
Okay, guys, chemically, how are they different? Ice crystals and hailstones. They are the same, right? So both of them are just as likely to be positively and negatively charged. Besides, does lightning ever occur without any hailstones coming down? Does lightning ever occur without any rain? Notice that it's a little bit more sophisticated of an explanation than you guys came up with, but still, it's lacking. We don't really have a good handle on this question. We really don't understand exactly why the top becomes positive charge and why the bottom becomes negative charge as far as the clouds are concerned. Okay, and that's not the only thing we don't understand. There's quite a bit that we don't understand regarding lightning, as you will find out. So what do we know? The initial ionization of the clouds will become, the initial ionization takes place because of friction among ice particles. We don't understand what causes further separation of the charges. We don't understand why the top of the clouds become positively charged, the bottom negatively charged. We know that the Earth is initially negatively charged. Somehow, magically, it becomes positive charged just before the lightning. All right, so speaking of separation of charges. Oh my God, this thing is working finally. Let's talk about something being positively charged, negatively charged, and neutral. Okay, so let's get back to the concept of net charge. What is net charge? Net charge is the sum total of all the charges that we are looking at. All right, so in this case, what is the net charge if I place a positive charge here? Okay, so now it's going to be -3, right? What's the net charge right now? It's going to be -2. What is the net charge? It's going to be -1. What's the net charge? It's going to be neutral. So now it's got equal number of positive and negative charges. What is the net charge now? It's got 5 positive charges and 4 negative charges, so now it's positive charge. Okay, so things can be positive charge, negative charge, as well as neutral. So you can charge something up positively, you can charge something up negatively, and also things can be neutral. All right, so question number 5, what's ionization? Separating electrons from atoms is known as ionization. So there are 3 ways we could do that: friction, heat, and light. What's the meaning of something being positively charged? More positive charges than negative charges. Meaning of something negatively charged means that it's got more negative charges than the positive charges. Meaning of something being neutral means it's got equal number of positive and negative charges. Question number 9, what process causes the clouds to become ionized?
Friction.
It's friction among ice particles. Question number 10. What process caused the charges to become further separated within the clouds after the initial ionization? It is a mystery. It's still an unknown. What makes a conductor and what makes an insulator? You guys are looking at the sodium atom. It's got 11 positive charges at the center. You got 11 negative charges moving about the center. So the net charge is going to be 0. So this is neutral. All right. So what would happen if you were to get rid of the outside charge? All right. So now it's got 11 positive charges and 10 negative charges. So this becomes positive charge, positive ion. So which means that the sodium is going to have a tendency to become positive charge in chemical reactions. You're looking at the fluorine atom. It's got non-positive charges and negative charges. So the net charge is neutral. It's all atoms will have equal number of positive and negative charges. Now, what would happen if you could just magically place a negative charge here? All right, so now it's going to have 10 negative charges and non-positive charges, but it's going to become negatively charged. So things could be positively or negatively charged, obviously, depending upon if they have more or less electrons. So the question is, why is that conductors are good at conducting and the insulators are not? All right, guys, it goes back to, the simple explanation is from classical physics. It's going to be related to something called the Octet Rule. Those of you guys who've taken chemistry, you would probably remember what the Octet Rule is. Okay, so what is the Octet Rule?
Electrons are happy if they have 8 or like 8 or 16 on the outside.
Okay, so octet means 8.
8 electrons.
Okay, I'll give you 5 points for that one. Guys, octet means 8, so we will use the 8 rule. All right, this is classical physics. A lot of the physics is made up. This is your Disney reality. A lot of what I'm about to say is not going to hold water when you get to modern physics. Okay, including the structure of the atom. All right, so octet rule is the 8 rule. According to chemistry, the atoms, the elements will get into chemical reactions in order to complete their outermost shells with 8 electrons. All right, so this is what drives chemistry. Any and every single element is going to get into chemical reactions in order to complete their valence shells with 8 electrons. All right, so here's a situation that we're looking at right now. Notice that we got 2 atoms right next to each other, and octet rule is unsatisfied. All right, in the outermost shell, the valence shell, this got 4 and this got 4. All right, so they want 8, but they got 4. So what do? Ideally, they like to complete the outermost shell with 8 electrons. It's not happening. And both of them got 4, and both of them will need 4 more electrons. So what do? What they do is they will electron share. All right, so in the outermost shells, the electrons will jump from one atom to the next one. These are known as the conduction electrons, so they're free to move. When the octet rule is not satisfied, when they have enough electrons in the outermost shell, I'm talking about the atoms, they do share these electrons. These electrons are going to be free to move from one atom to next atom. All right, so these are known as the conduction electrons, and the outermost shell is known as the valence shell. All right, so this is a made-up explanation from classical physics. So the octet rule is the tendency of the atoms to complete their valence shells up to 8 electrons. So that's what we're dealing with. Now the insulator. Oh, this one is 100% made up. I know it's 100% made up because I'm the one who made it up. I even said, hey, here's your Disney reality. So whatever the hell you guys do, don't memorize it. All right, so I'm going to give you an atomic structure, and then I'll make sure that the outermost shell is complete with 8 electrons. So the octet rule is satisfied. And then I'm going to call this material plastic. It's not. This is a noble gas. And somehow I'm going to go in there, and I'm just going to, through friction, I'm going to deposit some negative charges all over the place. Notice that these negative charges will not be able to attach themselves to any of the atoms, right? Because the octet rule is satisfied. Okay, so the insulators kind of work on this principle. When the octet rule is satisfied, the free electrons, when dropped, they got no place to go. When the octet rule is not satisfied, electrons are free to jump from atom to atom. They become conduction electrons. Okay, so that's the simplistic explanation that we will get to use from classical physics. All right, so conductors, octet rule is not satisfied. Valence shell electrons are being shared, which means that they're free to jump from atom to atom. Insulators, the octet rule is satisfied. Free electrons are not able to attach themselves to any of the atoms, so they got no place to go. All right, so the octet rule is satisfied. You end up getting insulators. All right, I'm not into you're white.
On an insulator, an electric charge stays where it is. But on a metal, it spreads out instantly. That is, the metal conducts electricity. On a deeper level, this is what happens. Each atom of a metal can be thought of as a positive ion with 1 or 2 loosely bound outer electrons. When 2 metallic atoms are very close together, the outermost electrons can pass easily from one to the next. As more atoms are added, electrons can range farther afield. Those mobile electrons are known as conduction electrons, and they give metals their special properties. In this way, all metals are electric conductors because every metal is like a giant molecule in which a number of electrons are shared equally by all the atoms.
Picture it as a structure of positively charged ions, glued together by a fluid of mobile electrons.
Okay, let me ask you this question.
As more the outermost electron. Those mobile electrons are known as conduction electrons because every metal is like a giant molecule.
Okay, so out of a 10-point scale, how would you rate the quality of this animation? I'm looking at it, having worked at an art school for almost 2 decades. This is not portfolio quality animation. If somebody submitted work like this, more than likely they would not be allowed to graduate. This is atrocious. This is horrible. I like it. I don't like it. Out of a 10-point scale, I would do a generous 1, and that's it. So the question is, why is the quality of this animation so bad? And as soon as I ask this question, what's the first thing that pops into your heads? The quality is really bad because?
It's an old movie.
Because it's old. Who said that?
Me, Isabella.
You said that. Why did you say it's old? Because it is old. This is from 1980s. Give yourself 5 points. You look at it, you say, yeah, it's not black and white, but it's still pretty old, right? Okay, so when they made this was made in 1985. It was actually considered the state of the art, guys. And today it's horrible. So that explains the low quality of the animation, because this was they didn't quite have the technology for this sort of stuff. But how about the music, for God's sake? Nathan is making a good point. What the hell is this? 1980s, they didn't have music back then? Are you kidding? And then you move on to 1990s, and then this is what you end up doing in 1990s. What is this? The sound effects. What show is this? Does anyone know? This clip is from where? Say it again?
Bill Nye?
It's from Bill Nye. Yeah, now you got 1990s, and you go from bad music to weird sound effects. All right, so now let's focus on physics. This comb is negatively charged. Does this mean that water is positively charged? Yes or no?
Yes.
Comb is negatively charged. Does this mean that water is positively charged? All right, let's test this. So when I was in graduate school, my dad was visiting. My dad is a medical doctor. He loves physics for whatever reason. And he also thinks that he's good at it. I don't know why he has that kind of weird confidence, because I don't think he is. So he said, Canon, do you know water is positively charged? I said, Dad, it's not. He said, yeah, it is. I said, Dad, it's not. He said, let me prove it to you. I said, go right ahead. So next thing you know, he's doing this demonstration. So I'm watching it. He said, comb is negatively charged, right? I said, yes, it is. And the opposites attract, right? I said, absolutely. So that means that the water is positively charged, right? I said, absolutely not. I said, Dad, we could do the same experiment a little bit differently. I said, just charge up the comb once again.
Hold the comb near the paper.
And then let's stop at this point. This is cute. All right, guys, paper, is it positive charge or negative charge, or is it neutral? I don't know. The paper, is positive charge or negative charge, or is it neutral? Okay, how can you tell? When you put, the reason why you see that, because I'm talking, it's causing some air currents. All right, so it changes the pressure in the middle. Notice that it's not attractive or repulsive, which means that the 2 pieces of paper, oh my God, I'm about to discover something. They're neutral. So if you charge up a comb negatively and then bring it near a piece of paper, what do you think is going to happen?
Hold the comb near the paper.
Oh, all of something magical happens. It becomes attracted to a negatively charged paper. Why? How is it possible to attract something neutral?
Hold the comb near the paper.
By using a charged object. You know everything is made up of atoms, right? You also know that the atoms are neutral, which means that within atoms, you will have equal number of positive and negative charges. So when you're using a negatively charged rod, what happens to the negative charges inside the atom? They will become repelled into the surface. What happens to the opposite charges? They will be pulled up to the surface. So which means that the surface is going to become polarized. All right, those of you guys, some of you guys were arguing water is naturally polar, which means that you have water molecules. Water is neutral. You got water molecules. One end of the molecule is going to be slightly negatively charged. The other end is slightly positively charged. So what happens to the molecules? They rotate. They spin around. All right, the molecules that carry the opposite charge is going to be closer to the negatively charged cone. All right, and neutral surfaces also will become polarized. Examples of it is if you get a negatively charged balloon and bring it near a wall, it's going to become attracted to a wall because the wall becomes polarized. Plastic is negatively charged by design.
Curing filler is matte glad cling wrap. Glad unrolls smooth and easy and clings tight when you...
Glass it's an insulator, right? It becomes polarized. Porcelain becomes polarized.
You need it to.
Of course, you got problems with metal pods. Metal is like a conductor, so it's going to take the negative charges from plastic and transfer them to the ground.
Yep. And clings tight.
Polarization, polarization, polarization. Remember I said the Earth is slightly negatively charged? So what happens to the Earth? Earth becomes positively charged through polarization. So after the charges become separated inside the clouds, and when the clouds become polarized for some reasons that we still don't understand, when the bottom of the clouds become negatively charged, the surface of the Earth becomes positively charged through polarization. So this brings us to the next question. Negatively charged comb is going to be able to attract pieces of paper, and the paper is neutral, which means that it's going to have equal number of positive and negative charges. Given the fact that the paper has equal number of positive and negative charges, how does a negatively charged comb able to attract paper? I'm going to give you 20 points for the best explanation. All right, I'm going to give you 3 more seconds. 3 more seconds to think about it. Okay, I'm not getting an explanation, so let me just elaborate. Like charges repel, right? And the unlike charges attract. Why is it that the force of attraction larger than the force of repulsion? That's what I'm asking. I mean, given the fact that the paper has equal number of positive and negative charges, why should the force of attraction be larger than the force of repulsion?
It's closer, right? Because the
Okay,
plus
so
and minus is closer
Nathan.
together.
Okay, so Nathan is making a good point. Nathan says because the opposite charges are closer, right? So which means that can we make the assumption that the electrostatic force is going to depend on the distance? Closer the charges are, the stronger the force is going to become, right? Immediately you make that assumption. Immediately you go, wait a minute, or else you would not be able to attract paper. Nathan, I'm going to give you 10 points for that one. The guy who actually made that connection first was this guy. His name is of the day. This guy who looks like Washington was Coulomb. So Coulomb is the guy who came up with the electrostatic force, the idea of the electrostatic force. And then he came up with this formula for the electrostatic force. So this is something that we need to discuss. All right, so Coulomb's law of the electrostatic force. This concept is very similar to the law of gravity that Newton came up with. All right, so let's just go over the law of gravity, the stuff that you guys are used to from physics 1. So Newton is the guy who came up with this. He realized that whatever this force is generated by the masses itself. All right, so you got the small mass, you got the big mass. So the product of these masses is the force is going to be proportional to the product of the masses, which means that bigger the multiplication is, the bigger the force is. He also discovered that with distance, the force is going to diminish. All right, so R represents the radial distance between the forces measured with respect to the center of mass. So larger the separation distance is, smaller the force is going to be. All right, so the force diminishes as the square of the distance. So you increase, okay, boom. So you increase the distance, the force is going to diminish. All right, so the force is going to diminish as the square of the distance. That's it. Capital G that you're looking at is going to give us the strength of gravity. Ooh. All right, so this will be the strength of gravity. Gravity that you're looking at, this is the strength of gravity. It's extremely, extremely, extremely small. Okay, so evidently I don't have it here, so let me write it down. Strength of gravity, capital G, the universal gravitational constant, is 6.67 times 10 to the minus 11. It's going to be expressed in terms of Newton meter squared per kilogram squared. That's it. All right, so here's the strength of gravity. Strength of gravity being 10 to the minus 11. Okay, is this a big force or a small force? 10 to the minus 11 is going to make it extremely small, which means that gravity is going to be extremely weak. All right, so Newton originally came up with this. So what did Coulomb do? Well, he comes up, he uses the same formula, except the mass becomes the net charge. All right, so you got 2 net charges, Q1 and Q2. R is the separation distance, which is going to be squared. So that's going to give you the electrostatic force. K is going to give you the strength of the electrostatic force, which is known as the electrostatic constant, which happens to be a really, really big number. All right, 10 to the $9. If you had that much money in your bank, how much money would that be?
$1 billion?
It would be $1 billion, guys. Okay, give yourself 2 points for that one. All right, so the strength of the electrostatic force is about $1 billion. And the strength of the gravitational force is 10 to the minus 11. It's almost 10 trillionth. That's really, really small. All right, so gravity is extremely weak. Electrostatic force is extremely strong. Okay, so I'm going to ask you a dumb little question. The question is this. The formulas, why do they look the same? Why do they look alike? Any ideas? This formula looks exactly like Newton's formula, looks exactly like the Coulomb's formula. Why do these formulas look so much alike? Coulomb ended up doing something that you're not supposed to do today. It's called plagiarism. Newton is the guy who originally came up with this formula. About a generation later, obviously Coulomb comes up with something that looks the same. Okay. The reason why we consider this plagiarism is because of the simple reason that you can make the assumption. Guys, just get it into your heads. Conceptually, you can make the assumption that the force is going to diminish with distance. There's nothing wrong with it. You can pull that out of your ass, and then you can make it stick. And it's going to stick just about anywhere, including the toilet paper. All right? You can make that assumption, and then you can say, hey, I just came up with it myself. I was just staring at the wall. I noticed that the force is going to diminish with distance, and that's it. You can make that argument. Here's the argument that you cannot make on your own. You cannot say under any circumstances that the force is going to diminish as the square of the distance. This is when you start to get into trouble, because this is not common sense at this point. You have to kind of justify that. As soon as you say, hey, the force is going to diminish as the square of the distance, you can't say, I'll pull that out of my ass and then make it stick. All right. You have to kind of justify why you think that the force is going to diminish as the square of the distance. Now, Newton, in order to make this argument, he had to invent calculus. That didn't come out of his ass. There was a lot of work behind it. We know, we talked about conductors, this and that. All right. Question number 17, what's electrostatic force? Electrostatic force is the force between charges. And how did Coulomb discover that the force decreased inversely with the distance? Obviously, for charged objects to be able to attract a piece of paper requires that the distance between like charges and unlike charges are important, so you can kind of guess at it from that perspective. So I'm going to leave it at that. Question number 18, how's the electrostatic force similar to Newton's law of gravity? Formulas look the same. Both of them are inverse square laws. They're going to be directly proportional to the product of the masses in gravity and product of the net charges in the electrostatic force. The difference is the gravity is only attractive. Electrostatic force could be attractive as well as repulsive. Also, the electrostatic force is going to be trillion times trillion stronger than the gravitational force. So electrostatic force is extremely strong. Gravity is extremely weak. So those are the major differences. Okay, so what does K represent again?
Coulombs constant.
Yeah, it's known as the Coulombs constant or electrostatic constant. Okay, one thing that I want you to know, and this is an important distinction which is going to come up time and time again, is the representation of the electrostatic constant. Okay, goof that up. All right, so K that we're looking at there. K can also be expressed in terms of a different constant. This is known as the space permittivity constant. Space permittivity constant is going to be a very small number. It's 10 to the minus 12. All right, so the question is, what does that represent? So K represents the strength of the electrostatic force when expressed in terms of epsilon. What does epsilon represent? In a strange sort of way, space permittivity constant is going to set a limit to how fast this force can travel in space. Do you get that? All right, so space is going to kind of put the brakes on in terms of how fast this force can get transmitted in space. That's what it means. All right, so which means that the force is going to have a speed limit. It's not going to go from point A to point B instantaneously. That's what it means. So the space is going to actually resist the motion or speed of this force. All right, so now that we talked about it, all right, so the formulas look the same. There's a little bit of plagiarism going on the part of Coulomb. It could be that the British and French didn't like each other that much. You can't get away with that sort of stuff. So what gives it away is the fact that both of them are inverse square laws. You cannot come up with an inverse square law just conceptually. That requires a mathematical justification behind it. Gravity is attractive. Electrostatic force can be repulsive as well as attractive. Electrostatic force is going to be much, much stronger than the gravitational force. So those are the major differences. Let's talk about the hydrogen atom. We're going to be talking about the hydrogen atom forever. Those of you guys who will take modern physics, you can actually see the evolution of physics through the hydrogen atom from classical physics into modern physics. All right, the first model of the hydrogen atom is known as the semiclassical model. That's the one that we use in chemistry usually, as well as electrical engineering. It's otherwise known as the planetary model. Notice that you have the proton, the positive charge at the center, the negative charge moves about it, kind of like the way the planets move about the sun. Niels Bohr is the guy who came up with it, worked on it for 2 years between 1911 and 1913 and published it in 1913. He won the Nobel Prize for it in 1922, and this is how the modern quantum theory actually got started. This is the first model of the hydrogen atom, or otherwise known as the semiclassical model, because it's called semiclassical because it uses the concepts from classical physics. This is not the model of the atom that we use in physics today. All right. So the only question that I'm going to have is, how fast does the electron need to be moving about the nucleus so it's not collapsing into the nucleus? All right, so this is the problem number 1 from the handout, otherwise known as the hydrogen atom problem. So we got the hydrogen atom. I'll set up the problem for you, and then we'll solve it. I don't want to spend more than 5 minutes working on it. All right, so here's the semiclassical model. You have the positive charge at the center. And moving about the center, you have the electron. It's going to be moving at a given speed. Electron is going to be located from the nucleus, certain radial distance. And we got a bunch of numbers that we will get to use. All right, let's use this. This is E. Electron is going to be a unit charge. It's going to be negative E. Make this Q1. This is going to be Q2. All right, so radius of the hydrogen atom is an experimental number. It's an observation. It's 5.29 times 10 to the minus 11. Okay, 5.29 times 10 to the minus 11. Okay, so I'm going to change that a little bit. I'm going to make it a little bit more exact. It's going to be 5.298 times 10 to the minus 10 meters. 5.29, 5.3, or is it 2.6? I don't remember. The only thing I'm going to say, the reason why this is important is because 10 to the minus 10 to the minus 10 meters, that term that we're looking at is known as angstrom. Okay, so it's a unit that we use in modern physics as well as in atomic physics. So the size of the hydrogen atom is half an angstrom. Okay, so we got two charges, Q1 and Q2. These are unit charges. We'll get to use 1.602 times 10 to the minus 19 Coulomb for that. We may need the mass of the electron, which is going to be 9.11 times 10 to the minus 31 kilograms. Okay, so the only thing I'm interested in is the speed of this charge. How fast is the electron moving inside the hydrogen atom? Maybe express it in terms of miles per hour. And just for the hell of it, also let's express it in terms of the light speed. Okay, so we got the radius, we got the unit charges, we got the mass of an electron. And let's figure out the speed of this. All right, now the solution. Okay, guys, how do you solve a problem like this? I need some suggestions. What do we do? Look at the motion. What kind of motion is this? It's circular motion, right? If it's circular motion, you have a generic expression for circular motion. Generic expression goes like this, which means that there's going to be a force which is going to be directed towards the center. You got the centripetal force. Okay, so what do we know? We know that it's circular motion, which means that there's going to be centripetal force. And we know what the centripetal force is in this case. All right, so the centripetal force in this case is going to be the electrostatic force. All right, so the electrostatic force is the force which is directed towards the center. So immediately you know how to do this. Okay, here's a generic expression for the centripetal force. And here's the expression for the electrostatic force. So you have Q1 times Q2 divided by the square of the distance. Okay, those of you guys who did not notice it, or you did, I don't know. There's something wrong here. What's wrong? All right, there's no square there. Okay, so we're done with that. All right, so the centripetal force is the same as the electrostatic force. So the electrostatic force is the centripetal force. So they will be equal to each other. All right, so K, Q1 times Q2 divided by R squared is going to be MV squared divided by R. Sum for V. Like terms will cancel. All right, so one of the R's will cancel. And then solve for V. All right, so when you solve it for V, what do you get? You have K, Q1 times Q2 divided by, it's going to be M, R. And then take the square root. All right, so Q1 is a net charge. This one is the positive one. Q2 is a unit charge. This is a negative unit charge. And then you got the electrostatic force constant. And you have E. And then you have negative E. You have the mass of the electron. You got the radius of the hydrogen atom. And then take the square root. All right, so K is our electrostatic force constant. It's going to be in terms of newtons meters squared per Coulomb squared. Okay, so I got my numbers. So the only thing we have to do is just plug everything into this formula and then we're done. Okay, so that's it.
Isn't that going to give us a negative number under the radical?
Okay, who said that? Okay, so Ian, you're saying it's going to give you a negative number under the radical. Absolutely, it's going to give you a negative number under the radical. So do we have a problem with that?
Sometimes.
I mean, in this case, definitely, right? Okay, so what's the problem with that?
Isn't there supposed to be absolute value marks around the charges?
No, I don't want to go there yet. What's wrong with what we have right now? Well, what's wrong with what we have right now is exactly what Ian was talking about. Do you want to have a negative inside a radical? Yes or no?
No.
No, not at this level. This is freshman physics, guys. You don't want to make it so complicated. You get a negative inside a radical, so what does it mean? Which means that you're done. There's nothing you could do with this. So how do you get rid of the negative? What is it that you have to do? I mean, I love the equation. I want to keep it. I don't want to give up at this one. It's too early to give up. All right, so how do we make it work if you have a negative? And then you go, wait a minute, I may be able to make it work. So how do you make it work? Why not just get rid of the negative? How do you get rid of the negative? What is it that you have to do? Okay, so here's what you need to do. Negative does not work. This equation, which is this one. Oh, I love this. It's modern art. I'm not going to change it. Gives you the force. It just gives you the value of the force, guys. This is not a vector. It's just a scalar. Do you get it? It tells you about the magnitude of the force, which means that the plus and minus signs don't matter. So what that means is you kind of have to get rid of the negatives. So how do you get rid of the negatives? You get rid of the negatives by taking the absolute value of the charges. So every time you see a formula like that, this formula is going to give you the magnitude of it. It doesn't give you the direction. So when you see signs, positive or negative, just get rid of them. So which means that you have to take the absolute value of these. As soon as you take the absolute value of those, the problem's solved. Okay, so all of a sudden we got an equation that looks like this. Okay, guys, plug the numbers in and check to see what you got. 2.1.
2.19 times 10 to the 6th.
10 to the 6th meters per second. So that's 2 million meters per second, right? Okay, let's do a quick conversion. Give yourself 2 points for that one. Okay, so let's do a quick conversion to miles per hour, just to give you an idea. So meters per second to miles per hour. 1 meter per second is the same as 2.24 miles per hour. Like units will cancel. Okay, so what does this give you?
I got like four. I got really large number. I got like 4,905,600.
Okay, so roughly about 5 million miles per hour, right?
Yeah.
Okay, so also I want someone to express this in terms of, so let's convert this to the speed of light real fast. What is this in terms of the light speed? So you go from meters per second to c. 1c is 300 million meters per second, right? So how fast is this? Roughly. So it's less than 1% of the light speed, right? Okay, cool. 0.0073. All right, so the number that I'm going to focus on is this one. So how fast is the electron moving while orbiting the hydrogen atom? Guys, it's like 5 million miles per hour. It's way faster than a Ford Tempo. 5 million miles per hour. That's how fast. All right, so I got a bunch of dumbass questions for you to answer. How does the electron know that how fast it needs to go in order to remain in an orbit around the hydrogen atom? How does it get up to the speed or slow down to the speed if it's moving faster than that? It's 5 million miles per hour, guys. Every single hydrogen atom is identical to every other hydrogen atom. Got it? How does the electron know how to get up to that speed if it's not moving at that speed to begin with? How does the electron know that this orbital is located half an angstrom away? Why not smaller or bigger? Why doesn't the electron collapse into the nucleus? Everything is identical, guys. These are the questions that you probably should have asked yourself when you were like 4 and forgot to ask these questions because you were really confused because the sky was blue and you didn't know why. I mean, this is the stuff you never asked. It's like, how does an electron know how to get up to the speed? How does an electron know where these orbitals are? All right, every single hydrogen atom is going to be identical to every other hydrogen atom. So if this electron is missing, it's going to get a new one, right? So if it's going to get a new one, the new one is going to be moving at exactly the same speed. So how do these charges know how to get up to that speed? How do these charges know where the orbitals are? And a lot of the classical physics is kind of made up. It's kind of cute. Question it too much. If you're curious about this sort of stuff, you may have to kind of major in physics. All right. If you're not curious about it, just stay in engineering. Just look at formulas and try to solve problems. All right. So physics is actually fascinating. All right. So this. Okay. So why do I have this? Okay.
Both give off light of the same color and have a crooked direction. Lightning and this discharge both give off a noise like a crack, and both are conducted by metals. The electricity generated in the laboratory is attracted to a pointed metal rod. Since they are similar in every other way, will lightning too be attracted to an iron rod? Let the experiment be made.
In the previous century, Newton drew a connection between the motion of the moon and a falling apple. In his century, a century later, Franklin drew the connection between sparks in his laboratory and lightning bolts in the sky.
Franklin hits on a method to prove experimentally that lightning and the sparks in his laboratory are exactly the same. They only differ in scale. The events of this fateful day are described by his close friend and fellow scientist, Joseph Priestley.
Secretly, because he was afraid of being made fun of, and with only his son as a witness, he raised a kite into an oncoming storm. Affixed upon it there was a pointed wire, which was to draw the lightning from the clouds. They were in the storm for a considerable amount of time with nothing happening. Then, just as he was about to give up, he put his knuckle to the key. Felt a definite electric spark. Can you imagine his excitement? The exquisite pleasure of that moment. He transferred the charge from the key to the electric jars. The jars could then be used to perform the same electrical experiments as if they had been charged by rubbing a glass in the laboratory. The sameness of the electrical matter with that of lightning had been proven.
All right, so Franklin's famous kite experiment. 2 questions. I'm going to give you 10 points for each. The first one is the obvious one. So what was the purpose of this experiment? Why did he feel the need to actually conduct an experiment?
In order to like prove that lightning is electricity.
Okay, so Bailey, he was trying to prove that the lightning is electricity. Okay, I need more. It's not bad so far. So he was trying to prove that lightning is what? Is the same as the
same as what he's producing in his lab.
Okay, both of you guys, I'm going to give you 10 points. So he was trying to prove that the lightning is the same phenomenon as the sparks that he was generating in his lab, right? So there was a purpose to the experiment if he had done the experiment. Okay, so the next question is, why did I say if he had done the experiment? Did he or did he not? Okay, so this one is a judgment call, all right? So we have to kind of have a discussion regarding this. So my question is, did he actually do the experiment or did he lie about it? Would we have a picture of a liar on a $100 bill? And if we do, what happens to the value of it? Is it worth as much as $100 if you have the picture of a liar?
Probably.
Probably.
Well, I mean, like he also did other stuff besides this, though.
All right, Bailey, you seem like you got an honest face.
Yeah.
So, what do you think? Can you trust a person like Franklin?
I mean, he had a lot of other contributions to the United States that I think outweigh if he lied about this. It kind of, I don't know.
So if he lied about this, what else do you think he lied about?
Right, like
guys,
the idea.
all right, guys, let's talk about Franklin briefly because this guy's my hero. My wife says that I'm gay about him. My wife is being a bitch. There's a good reason for it. All right, so daylight savings time, thanks to him. Aside from a billion other contributions, including library system, postal service, the fact that we print money, they printed money. I mean, this guy's contributions are enormous, right? So no one denies that this guy did a lot of good for the colonies.
Didn't he also own a couple slaves?
Oh, I don't think I don't think he was a slave owner. He didn't like that. It was against slavery.
Franklin was not a slave owner, but Washington. Skeletons in his basement.
Okay, Lucas, tell me about the skeletons in his basement.
Well, they dug at this site of where his house was, and they found a couple bodies, and they're supposedly theorized to be cadavers that he studied when he was trying to learn more about anatomy.
Okay, so Lucas, that was sick. When you said he's got some skeletons in his closet, most people talk about it figuratively. So now that we discovered, thanks to Lucas, that he was also a serial killer. All right, so moving forward. Here's a question for you guys. Simple question. Did he do the experiment or did he lie about it? What do you think?
I think he did it because, like, he's kind of famous and he got, like, everything. Like, he just loves learning science.
All right. Like, oh my God, this was awesome, man. Just get off Disney. Okay, so moving forward. Did he lie about it or did he actually do the experiment? The reason why I'm asking this question is, guys, if you were to do this experiment, chances are pretty good that you're not going to survive it. And how do we know that? Because the next 3 people who decided to do it precisely the way he described it, one guy was from Britain, he didn't survive it. The second guy was a Frenchman, he didn't survive it. The third guy was from Russia, he didn't survive it. All 3 got fried. All right. So none of those people survived it. We know today that if you were to conduct an experiment like that, you will not be able to survive something like that. So the question is, do you think he probably lied? Okay, so you guys obviously don't know your history, so let's talk about his son. His son was his bastard son. So he's the one who's flying the kite. So you're thinking, oh, this is a super late stage abortion, right? Is that what you guys are thinking? The wife wasn't very happy about it, so you're thinking, hey, here's the opportunity. By the way, guys, that son that I was talking about eventually became the governor of New Jersey. He was huge, very loyal to the king, and decided to remain extremely loyal to the king after the Declaration of Independence. All right, so it kind of fractured the relationship between father and son. So what happened to his son? He got arrested during the War of Independence. He spent the war years in a jail somewhere. And after the war, he had the option either to go to Canada, and most people, the Canada obviously remain loyal to Britain, so that's the reason why we have a border. He didn't even want to stay in Canada. He went to Britain and then spent the rest of his life there. These two did not speak to each other. His son's son, Franklin's grandson, Temple, is the one who went to France with Franklin, and he was growing up, so he mastered French really well, so he was part of the negotiations. It's kind of weird. The family history is weird. I mean, Franklin is the guy who was behind the ideals of uniting these colonies into the United States that we know of today, and his son remained loyal to Canada. And supposedly it was his son who was flying the kite. By the way, that never happened either. All right, more than likely he was lying about it. Was he the sort of person who would lie? Absolutely. How would I know that? Guys, this guy's a diplomat. What's the difference between a diplomat and a politician? The difference is when the politicians, when they speak, if you see their lips move, you know they're lying. Diplomats, you have no idea. And this guy was a diplomat's diplomat. And those people who end up helping the colonies to gain their independence, what happened in France is ideals of democracy end up spreading in France first, and then the people who help colonies gain their independence end up losing their heads. So it led to the 1789 revolution. And democracy is still spreading today, the ideas that himself started. So he was an amazing physicist. He knew his physics, but more than likely he lied about it.
You have a thundercloud with a positive charge sitting in the upper region, negative charge at lower altitude in the central region of the cloud. And the
all right, so this is beautiful. All right, so after the initial separation of the charges, for some unknown reason, the positive charges rise to the top, the negative charges sink to the bottom.
of those two charges creates a potential, a voltage of several hundred million volts.
These opposite
What's voltage or potential? They mean the same thing.
charged regions of
Okay, so we'll discuss that about a week
the
from now.
cloud are highly unstable and very attracted to each other. A lightning discharge is in some ways like a gigantic version of a common static electrical shock.
All right, now this is the discharge, right? So you got the positive ions capturing the electron. As soon as the electrons are captured,
When these sparks occur
it's going to generate sparks.
in the cloud, they are called intra-cloud lightning. When the negative charge in one cloud flows to the positive charge in another, the result is cloud-to-cloud discharge. Sometimes the negative charge in the ground, especially in tall structures, will jump directly to the positive charge in the top of the cloud.
All right, so notice that the Earth is slightly negatively charged. Bottom of the clouds are also negatively charged.
But
So the negative charge at the bottom
deadliest discharge
will polarize the surface.
are cloud-to-ground strikes. The Earth has a slightly negative charge, but the powerful negative charges at the base of the storm cloud
Okay, so I want you to take a look at the tree.
repel the negative charge,
Top of the tree is slightly negatively charged.
causing
Then it becomes
the
polarized.
ground to become positive.
This is exactly what happens to you as well. During a lightning storm, the top of your body will become positive charge through
When the
polarization.
attraction between these charges becomes strong enough, there is a spark.
So when it's strong enough, there is going to be a strike. Okay, good enough. I think it is. Nice. Damn, I mean, when you charge up this column, you're able to attract piece of paper, right? The question is how? How do you actually transmit the force without any physical contact between the charges? Newton faced the same question about a generation earlier. Force of gravity, does it extend all the way out to the moon? We had that discussion before, so the answer to that question is it must, right? How do we know that the force of gravity extends all the way out to the moon?
Because it is orbiting us.
Because if it didn't, what would happen to the moon?
It would
Straight line,
travel in a
constant
straight line.
speed. Very good. Give yourself 5 points. Straight line at a constant speed. Ali, also give yourself 5 points for the question. Your response. All right. Force of gravity must extend all the way out to the moon without any contact between the Earth and the moon, right? All right. So here's the problem, though, and this was a huge problem that Newton faced within his lifetime. British obviously was highly impressed with Newton because Newton himself was British. French, not so much. German didn't really care much for Newton himself either. All right, so it was a nationalistic sort of stuff. British and French, they thought that Newton was a genius mathematician. Physicists, not so much. Okay, so it took a little bit of convincing to realize that this guy was a genius. Okay, here's the problem that they had. They said, if the force of gravity extends all the way out to the moon, how does the force get transmitted? They had a valid point. Now, watch this class, guys. I'm about to do something magical. Nothing. I'm just going to move it. Oh, this is a lot of fun. All right, notice that I'm moving the glass this way and that way. So the glass moves in the direction of the applied force, right? You push it this way in the forward direction, you pull it in the opposite direction. So it's going to accelerate in the direction of the push as well as the pull. All right, so what happens if I go through the same motion without touching the glass? So I'm pushing on it, I'm not touching it, so the glass doesn't move. I'm pulling on it, I'm not touching it, the glass doesn't move. So what's the main requirement for you to be able to transfer a force? Contact, physical contact. So the physical contact is required for you to be able to transfer a force. So all of a sudden, these French as well as German physicists, they were skeptical. As far as they were concerned, this was action at a distance. It was just magical. They wanted to know how the force of gravity would extend all the way out to the moon and beyond, without the Earth touching the moon, without any sort of physical contact between the Earth and the moon. Newton, being a genius that he was, he came up with the best answer. When he was confronted with this question, he simply said, I have no idea. And he said, I feel no hypothesis, meaning that I don't have a theory. He had no explanation for him. He said, the only thing I know, gravity simply extends all the way out to the moon. Because the mathematics that he generated made some numeric predictions. The observations proved those predictions. That's it. Moon, instead of going in a straight line, it deviates from a straight line and falls onto a trajectory that matches the curvature of the surface of the Earth. It deviates from a straight line 1/20th of an inch per second, guys. That's the measured value, which agrees with Newton's theory of gravity, 100%. That's it. All right. If the mathematical prediction matches the observational fact, then the theory is good. So Newton said, my theory is good. I'm going to leave it up to the future generations to figure out how the force gets transmitted. Gravity extends all the way out to the moon. Gravity is a force, but how the force gets transmitted, I don't know, he said. I'm going to leave it up to the future generations. And the next generation of physicists came up with the force field idea. So the gravity extends all the way out to the moon and beyond as a force field. It's considered an instantaneous force by Newton. And we know today that the electric field does the same thing. Charges will attract or repel each other through an electrostatic force field, otherwise known as the electric field. You can map the electric field by using a positive charge or two positive charges or a positive and negative charge. Positive charges are considered to be the emitters, the radiators. The negative charges are known as the absorbers or the receivers. All right, so positive charge is going to emit the field. The negative charge is going to receive the field. Positive Q, negative Q, and that's it. All right, so the positive charge is the emitter. The electric field, electrostatic force field is going to be emitted by the positive charge. It's going to travel towards the negative charge at the light speed. So the positive charges are the emitters. The negative charges are the receivers, like the radio receivers. You got the transmitter here, which is the positive charge. You got the receiver here, which is the negative charge. All right, so electric field lines will start on the positive charges and they will end at the negative charges. Like charges will repel the positive, and unlike charges will attract.
Anywhere in the vicinity of an electric charge, a small test charge experiences a force. If it's due to only one charge, the pattern of forces detected by the test charge is simple. The pattern's more complex for two opposite charges. Or for two charges of the same sign.
All right, so the electric field lines will start on a positive charge and they will end on a negative charge. So they will always be directed away from the positive charges and they will always be directed towards the negative charges. So what'd you guys get for the force?
(4.81 times 10 to the negative 13).
Okay, 4.81 times 10 to the negative 13. Okay, who else got the same number?
I got that too.
Okay, good.
Well.
All right, those of you guys who
Yeah,
got
that
the
was
number, every single person who got it, give yourselves 2 points for that one. Okay, what you get for the acceleration?
5.3 times 10 to the 17th power.
5 point what?
3 times 10 to the 17th power.
Okay, so those of you guys who get this number, give yourselves 2 points. Okay, that's a huge acceleration, right? Okay, so what did you get for the speed? Okay.
5.83 times 10 to the 10th power.
Times 10 to the 10th power. Okay. All right, give yourself 2 points for that one. Okay, now express this in terms of the light speed. Immediately, you will notice something. All right, so light speed is 300 million meters per second, right? Okay, so when you express this in terms of the light speed, what do you get?
194 times the speed of light.
Yeah, 194.46. That's what I got.
Or roughly about 200 times the light speed, right? Roughly. Is that correct? All right. So those of you guys who came up with this number here, give yourselves 2 points. All right. So electrons moving 200 times the light speed. Does that explain where the light comes from? Yes or no? If something's moving faster than light, like flash, what happens? You will see light, right? It's moving so fast that you see nothing but light, correct?
Just seeing what.
Okay, if something's moving faster than light, what do you see?
Not a thing.
Not a. Yeah, if it's moving faster than light, it just creates light, right? When you put the brakes on, you know there's skid marks, correct? When you're driving, it's like the light is the skid marks of electrons moving faster than light. Got it? Yes or no?
Yeah.
Who's not happy? Isabella is happy with this. Who's not happy?
I'm not happy.
Okay, Nathan, what's your problem?
My problem is I don't think you can go 200 times the speed of light, or I don't think an electron can either.
Why not?
Because I thought light was like kind of like this, or the speed of light was some kind of universal max speed limit, something like that.
Electrons have mass. Wait. Did we make a mistake? Is the math wrong? What's the problem, guys?
The problem's wrong.
Everybody was getting the same number.
Wrong.
I love the fact that you guys are becoming more suspicious. Are you saying that the electrons cannot move faster than light speed?
Well, nothing faster than light speed, because like you'll get what you call it, the mass gets all messed up, right? Like the mass gets infinitely bigger, and it needs like infinite energy to be able to move it, so it wouldn't work.
Okay, Bailey, where'd you get that from?
I googled if you can go faster than the speed of light, so I was very curious, and it said no.
Oh, so you cheated?
I mean,
no. So
curious.
Curious is the way to go. So the Google gives you the wrong information, right? Google says the electrons cannot move faster than light.
Well, it didn't say electron. I'm saying in general something can move. I said in general something can. I didn't say electrons specifically.
Okay, so you're saying that the electrons cannot move faster than light. So if that's the case, where do you get the light from? All right, so something is wrong, guys. What's wrong with this is, what's wrong with classical physics? Oh my God, this doesn't make sense. Nothing with mass can move at the light speed or faster. All right, so those of you guys who made the argument that this is nonsense, give yourselves 5 points. This is nonsense. All right, that's the problem that you run into with classical physics. In classical physics, you got a hydrogen atom, you got the electrons located conveniently half an angstrom away, and they move at 5 million miles per hour. All right, it's classical physics BS. That's it. And a lot of the times, you guys do these problems blindly and come up with numbers and check these numbers up against the back of the book, and then as soon as you get the right answer, you just stop thinking that this is a math course. This is not a math course. You can do the math right, and still the numbers may be way off. And numbers are sensitive to the assumptions that you're making. Holy fucking shit! The assumptions that we were making, we made tons of assumptions here. All right, and we felt really good actually solving the problem because math is the easy part a lot of the times. There's a huge assumption here that I hate. Ever since I was an undergraduate student, I hated this assumption. The assumption is this, guys. This is a cute little assumption. According to this assumption, when the strength of the electric field is 3 million newtons per coulomb, that's when the lightning is going to strike. I wonder where they get that assumption from. A lot of the physics books are kind of BS. I kind of like physics books. If you're studying out, it's a good way to go. These are just reference books. And a lot of these little details are kind of made up. 3 million newtons per coulomb is the amount of electric field is needed in order to ionize the air, guys. Electric field strength never, ever fucking reaches that value. All right, there's no such thing. 3 million newtons per coulomb of the electric field strength. Are you kidding? I would be scared to get out of the house. That's like a fucking particle accelerator. No way, no way. No way. I would, you can't trust anything. I will lose my own electrons. Forget about losing your shit. All right. This is not a way to go. The strength of the electric field is only 10,000 newtons per coulomb, guys. Under lightning, that's it. This is the actual value. So, which means that electric field strength is never the right amount to cause lightning. So, if that's the case, what causes lightning? For lightning to occur, these positive charges need to be moving in the upward direction, and the negative charges should be coming from the clouds somehow. Where do you get the positive charges from, if that's the case? All right, so we got a bunch of mysteries. Mystery number one: strength of the electric field is not strong enough to cause lightning in reality. So there has to be something else that's initiating lightning. Bailey, Google that stuff. It should take you to Wikipedia, and then when you get to Wikipedia, you stop reading because you want to understand what it is that you're looking at, because that stuff is written by people like me. And on top of that, these positive charges are the ones coming out of the ground. Where do we get those positive charges from? The ground is polarized, guys. The charges are not separated. These phantom charges come out of the ground. Those are positive charges. So you got the positive charges going up, you got the negative charges coming down, and something weird happens. Let me explain what happens. So you got these positive charges coming from the ground. So you got the negative charges coming from the cloud, and the positive charges coming from the ground. Oh my God, now the lightning phenomena. So the ground becomes positive charge. That's just polarization. These charges are not individual charges, just positive charges. The ground becomes polarized to become positive. All right, and then you got these negative charges coming down in high concentrations, and these actual positive ions going up. What causes the ground to become ionized? That's, again, a mystery. Ground becomes polarized is not the same as it becomes ionized. All right, and then these charges meet, and when these charges meet, that's known as an electrical discharge. And then when there's an electrical discharge, the tremendous amount of energy is going to be released. All right, so let's talk about that. So you got these positive charges going up. All right, positive charge is a positive ion, and then you got the negative charges coming down. Okay, so this one is problem number 5. Okay, so what we need to do is we actually need to draw this out. All right, so a couple of things we know about this particle. Number one, we know its mass. Mass is given to you in terms of grams. All right, so let's express it in terms of kilograms. Okay, what else? We also know the charge. Oh, this is actually fairly big. All right, so this is millicoulombs, so we need to express it in terms of coulomb. Okay, so we know that there's an electric field along the x direction. It's 5 newtons per coulomb. There's nothing, no electric field along the y or z directions. All right, so this is, okay, so electric field strength here is uniform, so which means that the electric field is going to be constant. This particle is moving along the y direction. It's projected into the system along the y direction, so it's moving at a speed of 70 meters per second. And it doesn't have an x or the z components, so these components are 0. And so we want to know how fast this particle is moving 3 seconds later. So what is the speed of this particle? All right, it's 3 seconds. All right, this looks kind of nasty. All right, the way to do this sort of problem is you have to kind of draw things and then analyze it. So let me draw out my coordinate system first. All right, so I'm going to express this only 2-dimensionally. I don't care about a 3-dimensional system right now. Okay, so here's something. This is the x axis. You got the y axis. Electric field is going to be along the x direction. So we got the electric field in this direction. And then I'm noticing that the particle is going to be projected into this region along the y direction. So this thing is going to be moving along the y direction. All right, so I will have the particle. I'm just going to place the particle here. And it's going to be projected in this direction. All right, so this is the initial speed of this particle. All right, so what do you think is going to happen to the particle when you project it in that direction? All right, any ideas, any suggestions? What do we do?
It's going to accelerate to the right.
Okay, okay, that's not bad. It's going to accelerate to the right. So what's going to happen to this particle is electric field acting on it is going to cause a force on it, right? Along the x direction. So which means that this particle, this mass is going to accelerate to the right. Okay, very good. Okay, so what kind of motion is that?
Horizontal.
All right, so here's what's going to happen to it. It's gonna turn into a projectile motion in this direction. All right, so the trajectory is going to start to change because it's going to start to accelerate in that direction, which means that it's going to have a horizontal speed 3 seconds later. All right, so which means that if I place the particle 3 seconds later, it's going to be right here. So it's going to have the same vertical speed. So this speed is not going to change, right? This is the same as the initial speed. Now what's going to happen is it's going to be moving in this direction. It's going to accelerate in this direction. So it's going to have some speed in this direction. So if that's the case, can we figure out the actual speed?
Yes.
Yeah, so which means that you have to add up the vectors, right? So this is going to have a net speed here 3 seconds later. So the question is, what is this speed? Got it? Do you guys notice what happens when you actually do this visually? Okay, all of a sudden it doesn't look as bad. You kind of know how to do it. one way to attack these problems is just start out with an equation that has what you're looking for, whatever it is that you're solving in it. All right, so in this case, you're looking for the final speed, so come up with an equation that's going to have the final speed. In fact, here's the equation that has, here's the geometry that has the final speed in it, so that's the geometry that I'm going to use. So I'm just going to cheat at this point. I want to use this little thing to solve the problem. All right, so the easiest way to solve these problems, just make it visual if it's something that you can make visual. So here's what's happening 3 seconds later. All right, and I want to know what the final speed is, so that's my starting point. All right, so V in this case is going to be, all right, so you got the X component of the speed and you have the Y component of the speed. So take the X component of the speed, which is this, square it, and then take the Y component of the speed and square it. That's it. All right, so this is our final answer as is. So now let's fill in the gaps. All right, so what do we know? We know that the speed on the Y direction is not going to change. All right, so this is not going to change because there's no force acting in that direction. So we know that is the same as the initial speed, so it's not going to change. All right, so we're good with that. All right, so the problem is this. Okay, so what do we do with that one? Okay, now we have to come up with an equation for that one. Oh, okay, now what do we do? What equation can we use for that? I need some suggestions because I'm stuck. All right, so we need an equation on the X direction.
V0x plus AT.
Okay, say it again. Which one do you want to use?
V equals V naught X plus A times C.
Okay, so all of a sudden you're thinking, wait a minute, we got a bunch of equations that we can use. Once again, I noticed that you're focusing on the kinematics equations. All right,
Yeah.
so my question is always, why kinematics equations? Why are you guys using those equations? Because obviously you can use 3 equations. All right, that's one of the equations you can use. Here's the second one. And this is the third one, right? Okay, so I heard you say, you're saying that, hey, let's use this one. Okay, why do you want to use this one?
Because we already know the initial velocity and the time, and we can figure out the acceleration. So that will give us the final velocity.
Okay, I'm just gonna give you 5 points for everything that you said. The thing that I'm looking for is you should be saying I'm able to pick these equations because the assumption is that this is electric field is constant, right? If the electric field is constant, force is constant, so that gives you a constant acceleration. Okay, so only if the acceleration is constant, you can actually pick that equation, which is the correct equation to pick. All right, so very good. So if that's the case, all right, so if that's the case, let's use that one. All right, so under the circumstances, the best one to use is this one. I agree. Okay, so that was good thinking. All right, so initial speed is 0, you said. Oh, is it 0 along the X direction? Oh yeah, it's not moving along the X direction, right? Okay, so let me just adjust my notations here. All right, so initially it's not moving along the X direction, so that thing is gonna be 0. And now we got an expression. We got the acceleration on the X direction. Good, all right. So what do we do? So this and that, they're the same. So you can do a back substitution into that formula. And then we are done. All right, so here's the final speed. It's gonna be the acceleration on X direction. You got your T, which is gonna be 3 seconds. Velocity along the Y direction is the same as the velocity along the X direction. All right, so square both terms. That's it. All right. All right, let's check to see if we got everything that we need. All right, we're given a bunch of stuff, so let me grab these and check to see if we're done with the problem. All right, so what do we have? Okay, so we got the initial speed on the Y direction, so this is good. We're good with that. We got the time, which is T, right there. But the acceleration is not given to us. It gets complicated. So, which means that now we have to figure out the acceleration. All right, guys, one of the things that I want you to notice that I'm just using the numbers that I have to guide me, because whatever the final answer is, it needs to include all the numbers or most of the numbers given to us. All right, so which means that now we got to figure out this. Okay, so where do you get that from? You kind of get it from the force on the x direction, right? And where do you get the force from? You get the force from the electric field acting on the charge. Okay, so solve for the acceleration. So you have Q, you got the electric field along the x direction, and then everything's divided by the mass. And then we do our back substitution. All right, so this is the same as that. All right, so you have the charge, you got the strength of the electric field, the T is given to you. You got your mass, and you have the initial speed. All right, so this is a complete solution.
Video camera technology revealed that the anatomy of lightning is much more complex. This is the U.S. Air Force Atmospheric Research Center in Colorado Springs.
Our field of view lights up. That's the main part of the lightning strike that your eye will catch.
The new generation of cameras has enabled scientists to record a strike that lasts just a fraction of a second and play it back over 200 times slower to analyze its detail. These super slow motion images show the step leader making a connection with the ground. The entire charge then drains from the cloud above, seen as a series of pulses. Using the latest camera technology, scientists are beginning to unravel the mysteries of lightning.
So the negative charges that are coming from the clouds, okay, so they call them the step leaders, right? Okay, so what happens from their grounds? You got the positive charges will be coming up, positive ions coming up. These are known as the streamers. Well, obviously, what's initiating everything is what takes place inside the clouds, you could say. All right, so the step leader starts to come down, and the streamers will start to go up. When they make connection, that's when the lightning is born. Okay, now the streamers are positive ions, so we're not entirely sure what's causing the positive ions at this point. So that's another mystery. Step leaders, obviously, negative charges are coming down, and the streamers are positive ions going up, and when they make connections somehow magically, that's when you have the lightning. Okay, so question number 19. Why do we need the concept of an electric field? What purpose does it serve?
It helps us illustrate how a force can be applied without contact.
Okay, I'll give you 5 points for that one. It helps us to understand how you can transfer a force without any physical contact between the masses or charges. In this case, we're dealing with charges, right? Okay. What is question number 18? Forget that. Question number 17. What's electrostatic force? Electrostatic force is the force between charges, right? All right, so what is the relationship between the positive and negative charges to the electric field? All right, so what's the relationship of the electric field to a positive charge? You guys are looking at it, so here's the relationship. Positive charge is the emitter, negative charge is the receiver. So positive charge is going to emit the field, the negative charge is going to receive the field. All right, so the next question. What happens to a positive charge interacting with the electric field, and what happens to a negative charge interacting with the electric field? What happens to the positive charge interacting with the electric field? So here's a positive charge. What happens to it?
It'll accelerate in the direction of the field.
It's going to accelerate in the direction of the field. Very good. It's going to experience a force in the direction of the field, which is right here. And then it's going to accelerate in the direction of the field. All right, so what happens to it is it's going to experience a force. And as a result, it's going to accelerate in the direction of the field. So you got your force here. It's going to experience it. It's going to accelerate. So what happens to a negative charge interacting with an electric field?
It accelerates in the opposite direction.
Okay, very good. It's going to accelerate in the opposite direction of the electric field. So the positive charges will move in the direction of the electric field. The negative charges will move in the opposite direction of the electric field. So what happens to a neutral object interacting with an electric field? All right, so what happens to a neutral atom or a molecule interacting with an electric field? So you know that if it's neutral,
polarized.
Okay, very good. It's going to become polarized. It's going to have a positive and negative charge. So if you place it inside an electric field of some sort, electric field is going to push the positive charge in this direction, and it's going to pull the negative charge in the opposite direction, right? So what's going to happen is it's going to become polarized. All right, so one end is going to be negatively charged, the other end is going to be positively charged. All right, so that's what happens. It's going to become polarized. Okay, not bad. We got this positive charge, and let's have the electric field acting on it. Charge is positive. So the electric field acting on this charge is going to induce a force on it in the same direction. All right, so the charge is going to experience a force on it. So the electric field acting on this charge is going to induce a force on it. All right, so let's come up with an expression for the electric field. All right, and you have K, and let's assume that this is the source of the field. All right, source of the field is going to be Q naught. All right, so this is going to be the source of the field, which means that the Q naught is going to be located here somewhere. And this is a positive charge in this case. All right, so let's do a back substitution. So this is going to get substituted into that. So what do we have? K, Q naught times Q divided by Q R squared. All right, so notice that these two cancel. And now we get an expression for the strength of the electric field. All right, so the strength of the electric field in this case is this. You got this positive charge. All right, in this case, this is Q naught. And this one is the radiator, so it's going to be radiating the electric field lines. And R is going to be a radial distance that you're looking at. All right, so this is P is my reference point. I'm going to place my P right there. All right, this is my reference point that I'm looking at. So this is my radial distance. And so I'm interested in the strength of the electric field right at that point. So the strength of the electric field right at this point is going to be given by this equation. This is given by this equation. All right, so right at this point, you get the strength of the electric field. Guys, simply put, when you see this equation, it's going to give you the strength of the electric field of a point charge. All right, so this will give you the strength of the electric field of a point charge. So this equation, every time you see it, this is the strength of the electric field. This is the electrostatic force constant. This is the net charge. And this formula is going to give you the strength of the electric field at a radial distance away from the charge itself. Further away you get from the charge, weaker the field is going to become. Opposite is also true. Closer you get to the charge, stronger the field is going to be. All right. All right, so here's the radial distance, and here's the strength of the electric field is a function of the radial distance. So, which means that the strength of the electric field is going to diminish. Inversely is the square of the distance. All right, so it starts to go to zero, and it starts to go to zero fairly fast. That's what it means. All right, so when do you use this formula? You use this formula every time you have a point charge. So this is for a point charge. Something that looks like a point charge, it could be an atom, it could be a molecule, it could be a bunch of charges next to each other. So from outside, what looks like a point charge, if something looks like a point charge, this is the equation they use. All right, before I give you guys a break within the next 10 minutes. Okay, so I want to show you how to use this. I'm going to give you guys a few cases. All right, it's a really simple enough concept, except if you're not paying attention, it's really easy to get confused. Let's try to figure out the net electric field due to two charges on a line, just like that. All right, so I'm going to get a positive charge. I'm going to place the positive charge right here. I'm also going to get a negative charge and place the negative charge right here. All right, along the x direction somewhere. And then I'm going to have a reference point, P. This is my reference point, P, point of reference. Okay, so I'm going to be interested in the net electric field at that point. So which means that you have to find the total electric field at that point. Positive charge is the emitter, so electric field due to the positive charge is going to be pointing to the right at that point. So this is the direction of the positive electric field due to the positive charge. All right, the negative charge is a receiver, so the electric field due to the negative charge is going to be pointing to the left. All right, so the positive charge is pointing to the right, the negative charge is electric field due to the negative charge is going to be pointing to the left. All right, so now let's take a look at the net electric field at point P. So sum up the electric fields. I'm going to put P here, so it's going to be a point P. So that's our reference point. Okay, so positive charge, electric field due to the positive charge, which is this, is pointing to the right, so this is going to be positive. Electric field due to the negative charge, which is right here, is going to be, it's pointing to the left, so this one is going to be negative. Yeah. All right, so the next step is just fill in the gaps. For a point charge, this is what we get to use. This is the formula. All right, so this is your positive charge, this is your negative charge. R for the positive charge is going to be this distance. This is for the positive charge. All right, so for the positive charge, we have to use this. And for the negative charge, we get to use the same formula. All right, so for the negative charge, the distance this time is going to be this distance. And then you just sum them up. Okay, I'm ignoring the details. I'm just showing you how to set up these problems. We will do a problem though shortly. All right, so KQ. All right, let's make this Q1. Let's make this Q2. They don't have to have the same value. All right, Q1 and Q2. All right, so the only thing that they will have in common is K is going to be common to both of them, so I'm going to factor that out. So it's Q1, radial distance for the positive charge, Q2 divided by the radial distance squared for the negative charge. Okay, so this is a quick, fast example that I came up with. All right, so let's play this game one more time. This time, I'm not going to do the math. Let's just focus on the setup. Most of you guys usually get confused about this section. All right, so how do you know which direction this electric field is going due to a positive charge? And why is it that the electric field points in the opposite direction due to a negative charge? All right, so before we do one more example, guys, remember, positive charge is the emitter, right? It's going to be emit the electric field. And you also remember that the negative charge is the receiver. Okay, so this little detail is what's confusing you. Positive charge is the emitter, so the electric field is going to be pointing in this direction due to the positive charge. Therefore, right at this point, it's going to point to the right. Got it? And negative charge is a receiver, so which means that the electric field is going to be pointing towards the negative charge. Hence the reason why the electric field is pointing towards the negative charge. Got it? All right, so that's the visual that you need to have. All right, so let's do one more. Quick.
If you're right in the middle.
Okay, go back. All right, yes.
If you're going to put it in the middle, would it both point to the right then?
Okay, very good. Absolutely it would. Okay, so that would be a good example to look at. So let's do that. That's a couple of the concepts that I want to discuss. That's one of them. All right, so what would happen if you were to look at the electric field, total electric field right in the middle? All right, so let's place a reference point right here. Okay, and let's use that. Okay, so electric field due to a positive charge is going to point in this direction. And electric field due to a negative charge is also going to point in the same direction, right? Okay, so I think we kind of got disconnected. Okay, I got the. All right, I got disconnected here somehow. Okay, now this one is going to be important. I want you to just enjoy the complexity of the math. So we're going to be interested in the strength of the electric field due to a charge disk. All right, so this is going to be our charge disk. We're going to be interested in the strength of the electric field at point P. Okay, so the charge is going to be distributed onto the surface area, so we're going to just grab a small portion of it. This is known as the differential charge element, so a small portion. And we are going to be interested in the strength of the electric field at a radial distance from that net charge. And then we will locate this amount of charge, the small amount of charge that we are looking at, the differential charge, with respect to the center of our geometry. So this is going to locate the charge for us. This is going to be R prime. This is R. Don't get them confused. R prime is a displacement vector that's going to locate the charge for you. Okay, so Z is going to be the vertical distance. Capital R is the radius of the disk. All right, so this amount of charge is going to cause an electric field in that direction, along the radial direction. Okay, so we will get to use the generic equation for the electric field due to a point charge. And notice that you're just summing up all the point charges along that direction. And then you're looking at the contribution of the point charges to the electric field. And because the net charge is distributed over an area, so there's going to be a charge uniform surface charge density. So net charge is going to get expressed in terms of the uniform charge density. Once again, using the same ideas. Okay, if you're looking at the contribution of the charges on the surface area, it's going to give you some kind of, it's going to give you a region which is going to look like a cone, and the radial components will cancel out. So the only component that's going to survive is the Z component. All right, so the idea is the same as before. So the question is, now you got a differential area here, so how do you express the differential area before you set up your interval? Area for a circle is going to be pi r squared. If you express it in terms of the differential area, you have to differentiate both sides. When you do that, you guys should have learned this in Calc 2. So the area is going to be expressed in terms of the differential of r dr. So it gives you a vector, so what gets differentiated is r, so you're looking at only r prime in this case. All right, so r, you're looking at all the charges that go from 0. R prime is what you're looking at. R prime is going to go from 0 to capital R. So you're looking at the net charge within that area. So you do a little bit of calculus, which I'm skipping. Normally, I don't expect you guys to spend a lot of time doing calculus. Either you look it up or use some kind of calculus calculator. All right, so K is going to get expressed in terms of epsilon naught. Okay, so at this point, the only thing I'm really interested in the results. Okay, so I'm cleaning everything up. I'm doing the cancellations. So this is the final equation. We're not going to use this final equation as is. We're going to look at the implications of this equation. There are two cases that we're going to look at. Case number one, what is the strength of the electric field right at the surface? Okay, guys, when Z is 0, what do you get out of this? All right, so Z is going to be 0 here, Z is going to be 0 here. So what do you end up getting? So in the limit, the Z goes to 0. This entire portion goes to 0. This is the equation that you're left with. Okay, so what does that mean? Which means that the strength of the electric field right at the surface only depends on the charge density divided by 2 times that constant. That's it. Which means that the strength of the electric field right at the surface is going to be constant. All right, so for the charge insulating disk, like it could be rubber, it could be plastic, the strength of the electric field at the surface is going to be constant. Case number 2, make R extremely large, which means that you're dealing with an infinitely long disk, charge disk. If the charge is infinitely big, what would happen to the strength of the electric field? It's still going to remain constant. It's going to remain constant. This is for a charged insulating material. For a charged disk, if it's a metal disk, you get rid of 2. For a charged disk, the strength of the electric field is also going to remain constant. All right, so if the strength of the electric field remains constant for a charged disk, let's try to use this. Here's the sort of stuff that's going to kick your asses, guys. Here's what the math gives you. It says, here's the charge density. All right. For a charged disk, it's going to look like this. Question. Why is the strength of the electric field inside a charged disk constant? This charge. Notice that when the charge distribution is uniform, and that's exactly what it means, charges are equally distributed, right? So they will be equal distances to each other. Okay, so the electric field coming out of these charges will have components, and the radial components will cancel out. All right, so the components which are parallel to the surface will cancel out. So the only surviving component is going to be the perpendicular orthogonal component. And notice that the orthogonal components will be parallel to each other. Does that make sense? If it doesn't, you have to kind of think about it. All right, so you have to kind of start thinking about things visually. The math is one way of doing it, but you need to also know what the math represents. This is what the math says. If you have a uniform charge distribution, which means that the charges will be equidistances to each other, and every single component of the electric field is going to cancel out. Every single component parallel to the surface is going to cancel out. Every other component is going to cancel out, provided that this is an infinite disk, charge disk. The only surviving component is going to be the perpendicular component. Notice that there's a huge assumption here. What is the big assumption? The assumption is this is an infinite disk, which means that it's going to have a radius which is infinitely large. All right, so within those assumptions, the strength of the electric field is going to be constant. In reality, it's not going to be constant. Electric field is going to kind of leak out from the side in real life. It's going to have surviving components like that. Okay, and then it makes the mathematics complicated, so that's not the sort of system we deal with at this point.